In order to understand the chain rule for multivariable functions, let's go back and look at differentials and single variable functions. So if we have some function of a single variable, then in this case here, x is independent. So the amount of change of x when we change x is just the increment. There's no difference between the two. And sometimes this is written as x minus a when we move from the point a to some new point x. Okay, so the differential in the one variable case, df, is the partial derivative of f with respect to x, except we don't bother calling it a partial derivative because it's just a single variable function. So it's the derivative of f with respect to x times the x discrepancy, right? But then, as we've just seen, this can also be written as f prime of x dx. And in fact, just as a side note here, if we think of y as a function of f of x, so we use that notation, then this becomes dy is equal to f prime of x dx, which you recognize from integration, when you're doing integration by substitution. Perhaps you learned it as u substitution or change of parameters or change of variables. But it's when you do the substitution, you need to have that derivative involved, right? Okay, so now the picture that goes along with this is something like this. So here's A. A is this location on the horizontal axis here. X going that way. Here's F. And then we've got the tangent line. And so this formula right here is just telling us something about the slope. So here this is the f prime is giving us the slope. And then x minus a is how far we've gone in that direction. Okay, so yeah, so now say that x is actually a function of t. So our horizontal location depends on, say, time or something like that. Then we take this formula, and it becomes the derivative of f with respect to time is equal to, and then we've got f prime of x dx dt. So on the face of it, it looks like to get from this one to this one, we just divided by dt on both sides. And that's essentially what we did. Now, the interpretation is that in the first one here, we are talking about amounts. So we're talking about like the amount of change, and it's an approximation to the increment of f. It's not exact. In the second one here, we are talking about not amounts, but rates, because it's with respect to time. And in this case, it's exactly telling you how fast f is changing at a certain point. Okay, so now for the multivariable case, basically the same thing happens. The only real difference is now in this case we have dx is equal to delta x, and dy is equal to delta y, because now these are both our input variables. So in other words, they're independent. And so we're looking at, so if we start with our differential df, df is going to be f at this point, x minus a, fy at this point, y minus b. That's our differential. And then the derivative is going to be df dx times, now instead of dx, it's going to be dx dt. And we'll have our partial with respect to y times dy dt. And I guess I could have actually made this parallel a little bit more close by rewriting the differential first as df dx dx plus df dy dy as I was doing in the clips from the previous section. There we go. So now there's the chain rule, and you can see that it comes by essentially the same idea. And so again, we have the compare and contrast here, where with the differential, we are talking about amounts. Each of those quantities on either side of the equal sign is an amount, and it represents the approximate change in f near a point, as opposed to what's going on in the second one, where we're talking about rates. And this is talking about, this equation is expressing something about the exact rate of change of f at a point. So not near a point, but at a point.